Alright, so we are going to talk about the basics of calculus. Basics of calculus, there's two things. There's the derivative and the integral. And we're going to start with the derivative because the integral is just the opposite of a derivative. And we're going to talk about what the derivative is and what it's used for. Now, we are actually coming at this from a kind of helpful angle because we've already studied a bit of physics. So what we need to remember is, if you look at this position versus time graph, position on the y-axis, time on the x, the line of this, the slope of this, actually gives us some information. If you remember, is my little pen going to work? Let's try. It's not. Okay, let's go back. If you remember, let me hit that. Okay, yeah, red's good. I like red. Velocity is equal to the displacement over, let's just say, the change in time. So if I find the slope of this, the slope is, let's say, the rise, oh, that's not straight, over the run, that's not straight either. The rise is the change in x position, right? This is the x position, this is the change in time. So if you remember, the slope equals the velocity, right? The slope of a position versus time graph equals the velocity. And I'm reminding you that because it kind of goes into the whole fact that finding the slope of a graph, of a function, is actually very useful, especially in physics. So that's alright, that's nice and easy. It's a nice easy position versus time graph. But what if I have this? Alright, so what if I have a position versus time graph? This is still x. Okay, why weren't you right again? You would have thought you'd let me still write, wouldn't you? Okay, let's hit that again. Yep, okay. If this is a position versus time graph again, it's kind of harder to find the slope at any given point, right? Let's say I want to find the slope right here. Well, there's two ways you can do it. Well, one way to do it, but it's kind of hard to do. What you need to do to find the exact velocity at this point here, again, this is a position versus time graph, is, and I'm going to butcher this because I'm using my magic pen, but you've got to draw what's called a tangent line. Actually, that was not horrible. A tangent line is a line that only touches the function at one point. That's the point that we want to know the velocity for, right? So you draw a tangent line, and then once you have your tangent line, all you have to do is figure out the slope of this tangent line, again by the change in x over the change in t. Alright, so that's all you have to do, but it's very hard to do this without drawing it, and even then you've got to kind of get your ruler. So is there a way of doing it better? Well, I don't know, I think it was your man Isaac Newton. He was like the big driver behind calculus. I think for this exact problem, he realized that he couldn't draw a tangent line, but he could draw a secant line. Right, so what's a secant line? A secant line is, I don't know why I have two eyes there, that's dumb. A secant line is where you have a line that touches at the point that you want and then another point. So I'm just going to pick this point here. This right there is your secant line, not the straightest secant line, but it's a straight line that touches the point that we want, and I'm going to call this point x, and another point which is a distance h away. So actually this point here is going to be x plus h, right? Okay, so that's not so bad, but the thing is we have the function of x. By the way, forget that it's t right now. Just because I can't think of it any other way. This is y, alright, this is y, and this is x along here. Okay, forget its position, time, this is y, this is x, like a normal kind of mathematical graph, okay? So what he figured out is, I got the x position is x, the second position, like the second point, if you like, is x plus h away on the x-axis. Well, to get the y position, this is just going to be, all I have to do is plug it into this equation here. The equation is x, I don't know why it didn't do this right, x squared plus 2x. All I've got to do is plug it in here. So this is the function of x. And this point up here is the function of x plus h. Alright, so now if I want to find the slope of the secant line, all I have to do is do the old-fashioned slope equation, y2 minus y1 over x2 minus x1, and I'm good. So he said y2 is function of x plus h, function of x plus h, minus y1, which is the function of x, all over x2 is x plus h, minus x1, which is just x. And by the way, this x and then minus x, these are going to cancel out, right? Let's get rid of that. Let's get rid of that. So we have an equation for the secant line. All right, so let's play with this. I'm going to do this example on the next slide, and I'm going to plug it in, and we'll calculate the slope of this secant line. All right, so where was I? I got distracted. The bell went. All right, so I rewrote it up here. So the slope of this secant line is the function of x plus h minus the function of x. That's going to give me the delta y over basically x plus h minus x, but that just boils down to h. That gives us the slope of the secant line. So let's do it for this function where again I'm forgetting. Why does it keep doing that? Where I'm forgetting about the whole time and position. I'm just calling it x and y. It makes my life easier. So y is equal to x squared plus 2x. So let's plug this in. So what we're going to do is we're going to say the slope is equal to the function of x plus h. The function is x squared plus 2x. But what we got to do is we got to plug x plus h into there. So what we have is we have x plus h squared plus 2x plus h, right? And then we're going to subtract, I'm going to put it in parentheses, the whole function of x, which is just what we see here, x squared plus 2x, okay? And all of that is over h. Now, I'm going to change that x because I don't like it. I was back in England for a second there. And now what we're going to do is we're just going to basically expand, all right? So you got x plus h times x plus h. You've got to FOIL it, so we've got x squared plus xh plus xh plus h squared. So this is going to boil down to x squared plus xh plus xh. So that's going to be plus 2xh plus h squared. All right, so that's that bit expanded. And then it's going to be plus 2 times x plus 2 times h minus x squared minus 2x, right? Because the minus and the plus is going to be minus 2x. And then all of that is going to be over h. All right, so we are winning. That is a horrible division line. I'm going to draw another one. That's better. All over h. Now, we can tidy this up because actually if I'm looking at this, I've got an x squared right here, and I've got a negative x squared here. Let's get rid of it. All right, that's gone. I've got a 2x here, and I've got a negative 2x, right? So I can get rid of those. And what else have I got? I think that's about it. So what I am left with is I'm left with 2xh plus h squared plus 2h, and all of that is over h. But the beautiful thing is I've got an h here, I've got h squared here, I've got an h here. Let me go ahead and factor out an h real quick. So I've got h is equal to 2x, because I took the h out of that, I've got to take an h out of here, so it's an h, then it's going to be a plus 2, and then all of that is divided by h, and excuse me, my friend is right. Alright, sorry about that, now the h's cancel out, and this leaves me with the slope function is 2x plus h plus 2. Alright, this is the slope, so what this means is, if I know what the value of x is, I can plug it in. If I knew the value of h, I can plug it in, and I am good. However, this is the slope of the secant function. I don't know what h is, but I don't want the secant function. I want this tangent function that I just drew right here. And this is where the true genius of it all came through. In fact, I'm going to pause it and rewrite it on the next slide. Alright, so this gives us the slope, this function gives us the slope of the secant line if we know what x is, if we know the distance h, but we don't want the secant line, we want the tangent line here. This is a genius, because what your man Isaac Newton said, I believe it was him, let's just go with it, don't let the truth get in the way of a good story. What Isaac Newton said is, if this distance h gets smaller, then this line is going to be a little bit closer to the actual tangent line. If it gets, h gets smaller, if it gets smaller, you can kind of imagine the line kind of curving down. As it gets smaller and smaller and smaller, it's going to get closer to the actual secant line. And then, this is where the old limits comes in. He said, what if I set the limit as h approaches 0, when the distance h is 0, that secant line is actually going to be exactly the same as a tangent line. So what he says is we have to do the limit as h approaches 0 of tx plus h plus 2. Actually, it's nice and easy. All it's going to be is tx plus h, which is plug in as a 0, plus 2. And we have it. We have a function that gives us the slope of this function here. We have basically come up with the slope function. And again, this is beautiful because if the original function gave us the position as a function of time, by taking the derivative, we have now come up with a velocity function because the slope of a position function is a velocity function. So the slope function is 2x plus 2, which basically means at point equals 1, if I want to find the exact slope right here, all I've got to do is I've got to say 2 times 1 plus 2 is equal to 4. And that's the slope right here. If I wanted to find the slope right here at -3, it would be 2 times -3 plus 2, so it would be -6 plus 2 is equal to -4. Oh, look at that, symmetrical, didn't even mean that. And it gives us a slope function. Alright, so with that being said, do I want to keep all that? Discard it. Let me just ask you to practice this. Now, it's a pain in the butt. I'm not going to lie to you. It is an absolute pain in the butt, all of this work. And the good news is there is a real easy shortcut. But I want to see if we can figure this out later. So, remembering that the slope of a function is equal to the limit as h approaches 0. That's a weird 0. Almost turned into a theta there, didn't it? I keep doing theta. As h approaches 0 of f of x plus h minus f of x all over h. So what I want you to do is I want you to find the slope of these functions. I'm going to make them up on the spot. I'm going to do 2x squared plus 3x. I want you to find the slope of 9x. Yeah, that'll do. And then let's find the slope of, let's do a fun one, 4x squared minus 5x plus 9. Does that mean? Nah, I'll leave it like that. Could I do plus 9? Let me think. Yeah, let's do plus 9. Well, it's not going to hurt anyone, is it? Plus 9. Alright, there we go. I would like you to find the slope function, the derivative. In fact, let's call it the proper thing. Find the derivative of these functions. Now, the way we write it is this is y equals y equals. The way we do it, if you think that the derivative function is the slope is changing y over changing x, the actual nomenclature is dy over dx, or sometimes you just say dy dx. And that is going to be, this is the y function, so the derivative is the slope function of this, which is dy dx equals da-da-da-da-da. So you've got to go through this process. Pain in the butt. Remember, you've got to put the function of x plus h. So this x has to be x plus h, and you have to square it. This x has to be x plus h. Then you have to minus the function of x, which is just this whole function, divided by h. You should always be able to cancel out this h on the bottom. This is a good thing, because otherwise, if the 0 was here, if the h was still on the bottom and you take the limit, it's going to go up to infinity. Horrible stuff. So you should be able to cancel, factor out all the h's on the top and cancel it out, in theory. Good luck to you. So do this as your work for today, and then we'll talk about how we can make this easier moving forward. Alright, good luck. Bonne chance, buena suerte. Viel Glück, success. Buona suerte.